My name is Konstantin Schauwecker from Nerian Vision, which is a 3D camera manufacturer in Germany. And today I have the pleasure to give you a brief insight into some of the technology behind our 3D cameras. So to start with, why do we actually need 3D data? And the reason is that there are many image analysis tasks that tend to be quite hard if you only have 2D data available. And one of my favorite examples is this image of this box of cookies here, because on one of these stacks there's actually one cookie less than on the others. And identifying something like this by just looking at the two-dimensional image can be quite hard. But this task gets a lot easier if you have some 3D depth information available, because here you can now quite easily see that on this stack here, and there's one cookie missing compared to the others. So in the industry today, there are already a lot of 3D camera systems in use, and these are typically active 3D sensors that rely on projecting light for performing their measurements. So the dominant technologies here are time-of-flight cameras or structured light camera systems. Now, these active systems can work quite well, but there are some difficult situations with which they have problems. And these are bright ambient light, such as outdoors during bright sunshine. Also, they have a limited range up to which they can measure because they need to project their light far enough. And then these active systems often just run at low to medium frame rates. Now, there are certain applications for which these limitations pose a significant problem. And I try to collect some of these applications on this and the following slide. So first, there are autonomous vehicles or autonomous mobile robots that need to operate outdoors and thus are in contact with bright sunlight. Particularly for autonomous vehicles, they also want to perform long-range sensing in order to react early, and also sense at a high frame rate in order to have a fast reaction time. Another application is the measurement of large objects such as vehicles, stockpiles, wind turbines. These are again tasks that are performed outdoors and where you might encounter bright sunlight. And also these measurements are often performed from a distance because otherwise you can't fit such a large object within the field of view. Then there is occupational safety, where you don't want the camera systems to be easily disturbed by the lighting situation. And again, you want to have a high frame rate in order to enable a fast reaction time. And what we've been seeing more and more at Nerian are actually underwater applications, because this is an area where you cannot use the conventional infrared light-based active camera systems, because water is actually a very good absorber of infrared light. So what are the alternatives to active 3D sensing? This is passive 3D sensing by use of stereo vision, which is basically just mimicking on how we humans are able to perceive depth. Now, stereo vision copes quite well with bright light and many of the other difficult situations that we had on the slides before, but there's one significant disadvantage, and that is that the necessary image processing is actually quite computationally demanding. Now, in order to speed things up, we need to choose suitable hardware that is capable of massively parallel processing. And there are actually two options here. So first, we can use graphics processors or GPUs. Now, the advantage with GPUs is that they can be programmed comparatively easily, but they have a very high power consumption. Also, GPU-based systems typically require a very large form factor because actually you require an entire server. And this is why these GPU-based systems are typically not suitable for embedded use cases. The alternative to GPUs are field programmable gate arrays or FPGAs. Now, FPGAs typically only have a very low power consumption, typically consuming only a few watts. And you can build an FPGA-based system at a very small form factor. But the downside here is that the development process for FPGAs is particularly difficult and time-consuming. Nevertheless, we at Nerian opted for FPGAs as our technology platform. And we went ahead and implemented the entire stereo image processing chain on an FPGA. And the result of this work is what we can see here on the top picture on the left-hand side. This is the SceneScan 3D sensor system. It's an embedded system for stereo image processing that connects to, as here in this picture, our own stereo camera or to two conventional USB 3 vision cameras. And then on SceneScan, on the built-in FPGA, we perform all the image processing and then output through gigabit Ethernet the 3D depth data. And because the system relies on an FPGA for doing all the processing, the system has actually a very low power consumption of less than 10 watts. Now, let's look at some of the data that we get from the system. So this video that you see here was actually recorded outdoors during bright daylight, somewhere around Stuttgart. And as you can see here, we get these very dense depth measurements. So this, what we see is this is actually a color-coded depth map. In the next video, this is actually the same sequence just visualized differently now as a 3D point cloud. So every pixel from the depth map of the video before is now here projected as a 3D point, and we can again see how dense these 3D measurements are. So this is another example from an automotive use case. And here again we can see how dense these measurements are, and we can see both the road very close to the vehicle as well as the road very far ahead very nicely. And now here on the left hand side there's a bicyclist coming in, and this would be a typical application that you would want to detect here this bicyclist driver with a 3D camera sensor so that the vehicle can react accordingly. Now, some words about the algorithms that we run on the FPGA. Our image processing is based on our own variation of the semi-global matching or SGM algorithm. So the SGM algorithm applies an optimization process to identify which pixels from the left and right camera image correspond to each other and hence infer what depth a particular pixel is. Now, the original SGM algorithm is actually very unsuitable for execution on an FPGA. And this is why we had to do some extensive modifications of this algorithm. And in particular, we greatly reduced the memory bandwidth that this algorithm used. And only by these modifications, we've been able to implement this algorithm on an FPGA and achieve this high performance that you just witnessed in the videos before. But the stereo matching algorithm is not the only image processing step that runs on the FPGA. In fact, we run a very extensive post-processing chain after stereo matching. And in particular, there are two different types of filters that we run. First, we run filters on the 3D cost volume that is computed from stereo matching. And then we also run filters on the computed disparity maps, which is the inverse depth map that naturally results from stereo matching. And the filters that we run, they target different aims. So we have filters that identify image regions with a low confidence and mask these low confidence regions in the output data. Then we have filters for reducing the noise in the measurement data and filters for increasing the accuracy and the robustness. The speed from our FPGA implementation comes from massively parallel processing. So in SceneScan, we actually compare 32 pixels in parallel on every clock cycle. On top of that, we run 7 post-processing filters in parallel and 2 image pre-processing filters. The design itself is fully pipelined, which means that every processing element executes in parallel. Now, some words about the performance that we can actually achieve with this system. SceneScan is capable of processing approximately 30 million pixels per second. So this corresponds to a VGA resolution at 100 frames per second, 2 megapixels at 15 frames per second, or 3 megapixels at 7 frames per second. We can actually go all the way up to 6 megapixel image resolution. Our FPGA implementation actually also scales to much larger FPGAs and achieves even higher performance, and there will be some even higher performance systems coming out from us in the near future. And finally, some words about camera calibration. Calibration is very important for a stereo camera system. And the reason is that even minor mechanical deformations can really impact the image processing results. For us, this is even more of a problem because we allow the user to use any two USB 3 vision cameras, and thus we cannot influence how mechanically robust their mounting is. When doing camera calibration, what the user needs to do is he needs to take a lot of pictures of a calibration pattern from different viewing positions. And this can be a time-consuming task, but more importantly, this is often not possible if you have a system that has been deployed somewhere in the field where you cannot easily get to it. So we have spent a lot of time on making an automated camera recalibration work, and where the user does not have to do any interaction with the system and that constantly runs in the background and updates the calibration information. So I want to give you some brief insight on how this actually works. We have one example stereo camera frame here at the bottom. And what we do is we actually identify natural landmark features in both images. And then we perform a matching between these two images without actually requiring an exact camera calibration. And then from these matches, we can compute an update to the extrinsic camera calibration, which is actually the weakest parameter in the calibration data. So much about the technology behind our systems. Now I want to take a look at some actual applications. Now the list here is a little biased towards academic projects, and the reason is that with industrial projects we typically have NDAs in place that prevent us from talking about them, but we're free to talk about all academic projects. So for the start, Nerian sponsored 2 teams at the 2019 Formula Student competition. So Formula Student is a competition for student teams to build race cars, and they have one competition where the teams actually build autonomous race cars. And we sponsored 2 teams for this competition. One team was a joint team by TU Delft and MIT that actually achieved 3rd place out of 20 at the main competition. And we also sponsored a team from the University of Stuttgart that ranked 6th out of 20. And we also sponsored University of Stuttgart for this year, but unfortunately the event was cancelled due to COVID-19. Now, I have a video here of one of the runs from the joint MIT-TU Delft team, and so this is their vehicle. And the stereo camera is actually located in the top assembly of the vehicle. And on top of stereo cameras, they also used other sensors, so you might be able to spot the LiDAR sensor in the front, and they relied on a fusion of different sensors for making their vehicle act autonomously. Then here's an example of a smaller autonomous vehicle that was built by the University of Tübingen. There again we see there's a stereo camera on top and also a small LiDAR system. The University of Tübingen used this robot to implement a person following, and so the system that they developed even works at a fast running pace, and it follows the person in a collision-free path and even works in a very dynamic environments. Then we also had various customers that put our camera systems on drones or unmanned aerial vehicles. On the left-hand side, we have again one system from the University of Tübingen that actually used 2 stereo camera pairs for flying autonomously. On the right-hand side is one example from Carnegie Mellon University, and they used this unmanned aerial vehicle for demonstrating in-flight obstacle avoidance by using stereo cameras for sensing these obstacles. What we see here, this is an autonomous underwater vehicle that was built by Michigan Tech Research Institute and the United States Geological Survey. As I said before, water is a very good absorber of infrared light, which is why they were not able to use any other 3D camera technology. One thing to keep in mind when using stereo vision underwater is that water actually changes the light refraction. And this is why when you perform camera calibration, you actually also need to perform the calibration underwater. And this is actually what we see here in this image where they performed the camera calibration in a swimming pool. Then what we see here is an example for robotic manipulation by the University of Stuttgart. The robotic gripper that we see here in the image is being used to manipulate a flexible object such as a cable or a flexible tube. Now what the University of Stuttgart did here is they used our stereo cameras for detecting this tube, and then they ran a physics simulation to perform the motion planning. And this system was actually displayed at last year's SPS Nuremberg trade show. And this is a video that I myself recorded there at the trade show, and we can see that the robot gripper is gripping this tube and moving it to a defined orientation that was before specified by the operator. And the stereo camera is actually looking down onto the tube at an angle from the top corner. So here we can see it. And further to the right is actually the operation terminal, where the user can specify the orientation that he wants, and we can also see where the system detects the tube to be. On this slide here we see an interactive floor projection that was built for a shopping mall in Singapore. Now the makers of this installation faced some particular problems because the cameras are actually very high up above the ground, so they have a distance of 13 meters. Also, the projection size is very large, with 13 by 10 meters, which is why using conventional 3D cameras has been very difficult. But we supplied them with a stereo camera system with a very wide baseline distance, which is thus very suitable for long-range sensing. Here's a video of the system in operation. The person walking around here picks up these puzzle pieces and moves them just with his body movements. And so shoppers can actually play these simple games while they are on the wall just by moving around. So to conclude, I think that stereo vision is a compelling technology for 3D sensing, and particularly for challenging environments it poses significant advantages. So stereo vision works well in outdoor situations, for long-range measurements, and even for underwater applications. Thanks to FPGAs, we can actually do stereo vision at high frame rates in real time. And FPGAs also enable this technology to be used on embedded systems. So with that, I'm at the end of my presentation. If you have any questions about the material presented, then please send an email to service@nerian.com or just go to our website www.nerian.com and fill out the contact form. Thank you.